For a larger gravitational force, do we want more or less mass, and do we want more or less distance? So we're trying to look at this equation. If I want this force, the capital F, to be bigger, that means I want bigger numbers on top, so I want a bigger mass, more mass. And you're dividing by r to get the force, so you don't want to divide by a bigger distance, that would make it smaller, and we want a larger force, so we'd want to divide by less distance. Just think about, you want big numbers on top and dividing by smaller numbers, so bigger mass and less distance r. Which one has a greater impact on the force of gravity, mass or distance? Definitely distance, because r squared. So if I were to double the mass, that'd be a factor of 2 bigger. If I double the distance, that'd actually be a factor of 4 smaller. How would the gravitational force between the Earth and the Moon differ if the Moon was twice as far? So twice the distance is 2 times the radius. So if I were to plug in, keep the masses the same, but I plug in twice the distance, remember r gets squared, so that's a factor of 4, but that's on the bottom. On top we have a factor of 1 because nothing happens, so it would decrease by a factor of 1/4, be 1/4 smaller, times 1/4. Tell by what factor the force would change, including bigger or smaller, if the following happened. So if I have 3 times the mass and 3 times the distance, that's going to be times 3 over 9, which is times 1/3. Multiplying by 1/3 is getting smaller. If the mass of one is tripled and the other mass is doubled, so that's multiplying 3 times 2, so that gives me 6 on top and nothing on bottom, so that would be 6 times bigger. Both masses are tripled, so 3m, 3m, and the distance is halved, like this. So that's a factor of 9 on top, and then we want to be careful here, because 1/2 squared, and we need to put parentheses around it, is actually like 0.25. So then 9, or you can do it all at once, 9 over parentheses 1/2 squared. That gives me 36, so times 36 bigger. Both masses are tripled, and the distance is doubled. So that's a factor of, ooh, that pen sucks, 9 on top. 2 squared is 4, so that would just be times 9/4. 9 divided by 4 is still getting bigger, so 9/4 bigger. 2 steel balls are a distance x from each other as the mass of one is doubled, and the distance is reduced in half. R, like that. And then the gravitational force between them is, so again, try to find the factor that it's changing by. So that's 2 over, I just put it all at once, 2 divided by 1/2 squared, and that's going to give me times 8. So 8 times is great. On a planet with twice the radius and twice the mass, your weight, so double one mass, double the radius, so that's a factor of 2 over 4, so that's a factor of 1/2 as much. Now 1/2 smaller isn't your answer, because I want to know what is my new weight. Well, if my old weight is 40 and it's getting halved, then my new weight is just 20. 2 objects with a gravitational force of 25 newtons are 2 meters apart. When they are moved to 14 meters apart, what is the new force? So this is a what would happen question. This is my old force, and I want to know my new force. So we look, what is it that's changing? Well, your distance, or your r, is going from 2 to 14, which means I'm 7 times the radius. Now the typical mistake people make here is they're like, oh, 7 times, and they multiply this by 7. That's actually not what's happening. You're getting 7 times the distance, and you're looking for how much the force is changing. We'll plug in same masses, but 7 times the distance. That's actually going to give me 1/49th the force. So then, now I'm saying, okay, my old force is 25, and I'm getting 1/49th the force. So then you just multiply, and that gives you like 0.51. That would be your answer. So a similar thing to this would be like up here when I said, okay, twice the distance. Your answer wasn't twice the distance is twice the force. Twice the distance is actually 1/4 the force. So here, when I give you 2 to 14, that's 7 times the distance, you need to figure out how many times smaller or bigger the force is from that. And then multiply. Alright, if the moon was only half as far, then the force would be, so first of all, if it's half as far, that's going to be closer together. Closer together is for sure going to be a bigger force. We can cross off A and C. Now we plug in halves, the distance, so 1/2 r squared. It's tempting to just be like, oh, that's 1/4, but actually this is a 1 on top over the 1/2 squared. So if we go to our calculator, 1 over 1/2 squared, that's going to give me 4. So it's 4 times 4. Alright, two objects each with a mass of this produce a gravitational force between them of this. So this is M1, M2, that's F, and I'm looking for R. So we're going to plug into our force equation, G M1, M2 over R squared. So my force is 3.7 times 10 to the negative 6 equals G, which is 6.7 times 10 to negative 11 times both masses are this over R squared, which is what I'm looking for. So I'm going to type the top part into my calculator. Times. So that gives me 4.1875 e negative 4, like this. 3.7 e negative 6. Now I have an unknown on the bottom, and I don't like that, so I'm going to multiply that up like this. That crosses off. Now it's over here. So then I'm going to divide this one over. I'm running out of space. So then dividing the 3.7 e negative 6 over, that gives me 113. So I have r squared, because we crossed that off now, r squared is equal to 113.17. And now I'm not done, because that's what r squared is. I want r, so I take this square root of that. That's going to give me R is 10.64 meters. Okay. The gravitational force between two objects, each with a mass, so again, this is M1 and M2, because they both have that mass when they are separated by this distance. This one is straight plug-in jug, G M1, M2 over R squared, 6.7 E negative 11, mass of 3.1 E5, and another, the same mass, divided by 2 E3. Don't forget to square the R. Times 3.1 E5 times 3.1 E5 divided by 2 E3 squared. And that gives you a force of gravity of 1.81 E negative 6 newtons. 817. Just like that, that's fine. An object weighing 80 newtons on the Earth's surface would only weigh 20 newtons when its distance is. So I'm going from 80 newtons to 20 newtons, so that's going to be 1/4 of the force. Now the question is, how would I get 1/4 of the force? Well, a smaller force is only going to come when I'm farther away, so getting closer, halving the distance or 1/4ing it doesn't make sense. Quadrupling the distance doesn't make sense either, because if I were to plug in 4 squared, that would actually be 1/16 of the force. So I'm going to use double like this, and then just double check. That would give me 1/4, which would be 1/4 the force. If it was 80, 1/4 of that would be 20 now. Yeah, doubling the distance checks out. An object weighs 100 newtons on the Earth's surface when it is moved to a point that is 1 Earth radius away, or twice the original distance. So, kind of already know, it's the above question, but twice the distance, R gets squared, so that's 1/4 smaller. If my old force was 100 newtons and I get 1/4, oh my gosh, I sound so ridiculous right now, this nose, that's going to give me 25 newtons. What would happen to the gravitational force if the mass of a planet and its sun were both doubled? So I'm doubling the mass of each, and it doesn't say anything about R, so that's going to be a factor of 4 bigger, so it'll increase by a factor of 4. Which of the following would make you weigh half as much as you do now? If I move to twice the distance, well, looking at both questions above, twice the distance actually gives me 1/4 the force. Remember, weight is just force, so that doesn't make sense. If I take away half the Earth's mass, that would be halving one of the masses, keeping everything else the same. That would be 1/2, so that's true. Halving the distance would make it a bigger force, not smaller, so that doesn't make sense. At which point would a spacecraft traveling from the Earth to the moon experience a gravitational force from the Earth that is equal to that as the moon? So I want to know at what point would the force towards the Earth and the force towards the moon be equal? Now it's tempting to say B because you're like, oh, it's equal distance. But if you look at your force of gravity equation, it depends on lots of things, right? It depends on the masses and the distance. So at this halfway point B, the forces would not be equal. It would feel a bigger force towards the Earth because the Earth has a greater mass. So the point where it would be balanced would be C. Because I'm closer to here, I'm closer to the smaller mass, and then I'm farther away from the bigger mass. So the Earth might have a bigger mass, but it's also farther away at that point, so that would balance out. So at point C, because it's farther from the Earth, and the Earth is more massive. The points are not all the same because you still feel a force of gravity in space, right? The moon feels a force of gravity with the Earth. You have to get really, really, really far away for that to be negligible. Satellite B has twice the mass of satellite A, which one feels a stronger gravitational attraction, like gravitational force, with the Earth. Well, this is G m1 m2 over r squared. G is a constant. First mass would be the mass of the Earth. They're the same distance away, but the second mass matters. So because it has twice the mass, it would have twice the force. So B, because it has more mass. What if satellite B was twice as far from the Earth as satellite B, as well as, okay, whew. Now it is twice as far away as well as twice the mass, so now B isn't there anymore. It's like around like this. Which one would have a stronger gravitational attraction, a stronger force now? Well, A would be like your m over r squared. For B, now you have twice the mass, and you also have twice the radius. Those do not cancel out because r gets squared, so that's a factor of 2 over 4, which is 1/2 as much. So the one with this is for A, this one is for B. So the one that has a stronger gravitational attraction is actually A. Because yes, this one had twice the mass, but if you go for twice the distance, that actually will end up being smaller. When Earth and Moon are separated by a distance of this, so that's my r, the magnitude of the gravitational force is this. What would be the magnitude of the gravitational force if they were separated by this? So this is my old force, and I want to know what is my new force. This is a what would happen question. So I'm looking at what's changing. In this case, it's the distance. I'm going from 4 times 10 to the 8 to 8 times 10 to the 8. So that is doubling the distance. So if I have times 2r, well, you might already know this from like the 4 questions above, but if I double the radius, that's a factor of 1/4 smaller force. So if this is my old force to E20, I just need to multiply it by 1/4. And that gives me my answer, 5e19 newtons. So very similar to what we were doing for number 7. We're looking, there's something changing, so this is what would happen. It's going from 4 times 10 to the 8 to 8 times 10 to the 8. That's doubling the distance. And then we said, okay, doubling the distance, keeping the masses the same, that's 1/4 of the force. So take my old force and 1/4. Two objects are attracted to each other by a gravitational force F if one mass is doubled and the other is tripled without changing the distance. What's happening to the gravitational force? Well, 2 times 3 is 6. That's 1, so it's getting 6 times bigger. Phobos, a moon on the planet Mars, has an orbital radius, that's my r. It has an orbital period, t. Determine the mass of Mars based on this data. So if we look, we have r and t. That, I'm going to use this equation. That's going to get me v. So I'm going to plug in t equals 2 pi r over v. 27,561, 2 pi r, is that big number, over v. So I'm going to put that into my calculator, 2 pi times the r. That's a very large number. Over v equals the 27,561. All right, now my unknown is on the bottom, so I'm going to multiply that up like this. And then I need to divide the 27,561 over. And that's going to give me That gives me that my velocity is 2138 meters per second. Now careful, because that's actually not my answer. I want to know my mass. Now I need this to find my mass, so I'm going to look at this equation right here. Now I'm trying to find m. You can substitute in right now and then rearrange. I find it easiest to rearrange first and then just substitute in, because it just gets annoying rearranging huge numbers. So if we're trying to get m by itself, first we need to get rid of the square root. So we're going to square everything, and that's going to, I'm do my work up here because I'm going to run out of space. That's going to give me v squared, and then here the square root and the square will cancel, gm over r. I'm going to multiply the r up, and then to get m by itself, I just divide the g over. And then now I can just plug in, m is r v squared over g. We said r was 9380, 123. Velocity is 2138 squared over g, which is 6.7 e negative 11. And now you just type. And that gives me that my mass is 6.35 times 10 to the 22 kilograms, which is a very large number, which makes sense for a planet.